I am Tim Moore. I'm an engineer at Cesium. I feel like I've been doing terrain visualization since the 90s, but it's a lot more fun today because things are a lot more detailed. And I'm going to talk about the Cesium Native library. And so what is it? Well, it's a library you can look at GitHub. And it has several components to it. It is a very complete reader and writer of glTF. And let's say it's a very complete reader and somewhat incomplete writer of 3D tiles. And it has a sophisticated algorithm for selecting the tiles that might be in view in a graphical application and rendering them and scheduling their loading. And in addition to that, it has quite a bit of support for dealing with geometry and geospatial computations. And it was originally written in order to support the the application of Cesium for Unreal, which is our plugin for Unreal, and which necessitates, of course, streaming 3D tiles in real time into Unreal, which is sort of a challenge. And the key point of Cesium Native is that 3D tiles is really just wrap glTF. There's some funky formats in 3D tiles 1.0, but they're really wrappers around glTF, and in some cases they're kind of redundant today as glTF has evolved and subsumes some of the functionality that's in 3D tiles. And ideally, a client that wants to render 3D tiles only has to understand glTF. That's kind of the happy result of Cesium Native. And even though Cesium Native does support a bunch of other formats, in particular, Cesium World Terrain is in an older format called Quantized Mesh, the application doesn't care. I, in fact, didn't realize that Cesium World Terrain was in Quantized Mesh until I was well into writing an application using Cesium Native. And the other formats, too, that are part of 3D tiles, like the points format, is translated into glTF for the benefit of an application. And so this is the result. I can say modestly an excellent glTF reader and writer, although I had nothing to do with it, but it is. And it reads and writes 3D tiles. And it does this all asynchronously. This is complicated, but it's essential an asynchronous problem. You want to be streaming 3D tiles while your application chugs along, and it does that. And it's intimidating, but it really is quite straightforward to write a visual application that uses Cesium Native and displays 3D tiles. And as long as your application can render glTF, well, you're really almost there. And so it admits a bunch of possible uses, and the obvious one is visualization. And it's used in Cesium's native projects, the Unreal, Unity, and our Omniverse plugin. And now a bunch of third-party ones too. I mentioned VSGCS, which we'll look at as an example. The recently released 3D tiles for Godot uses Cesium Native in its implementation. Also, I forgot to mention the OSG Earth 3D tile support is done using Cesium Native as well. And those latter two were funded by Cesium with ecosystem grants. And Danielle said we really encourage people to use it if you're going to do a native port. Another use is going the other way for doing I/O with 3D tiles. This is gaining more traction at Cesium to use Cesium Native to actually write out our 3D tiles in glTF. Cesium Native is relatively new compared to those tilers, but it is gaining traction there. And so just generally using Cesium Native for utilities that might deal with glTF and 3D tiles is useful to process them in interesting ways, and as well as doing geospatial stuff. I say coordinate conversion here. We have a lot of support for lat-long to earth-centered and simple datum shifts without using the gigantic libproj, which you may have heard of. In order to dive in to using it, we require a couple of things that aren't supplied or were not supplied until recently. One is the ability to do something asynchronously. And this is a dependency because, for instance, in Cesium for Unreal, you can't just go off and start your own thread. You really want to integrate with the game engine's thread management. And same for doing stuff over the network. You can't just go out and do stuff on the network. You really want to make HTTP requests using the support of the environment you're in. And game engines or whatever usually have good support for doing these things well. But if you don't want to do that, you're starting from scratch, well, here is perhaps the simplest task processor to start a task. I took this code out of test code in Cesium Native. It would work fine. It might not be the most efficient, but hey, it will work. In real life, you'd want thread pools. You wouldn't want to just start up a thread for every single thing, but this would do. The other thing is a thing called an asset accessor, which is actually not a trivial piece of code to go do HTTP requests and puts as well. But we now include an example of that in Cesium Native, and you don't have to go write this yourself. You can use a thing called Cesium curl, which will be released at the end of the month. And that evolved from code we wrote at Cesium to do this and is used, it was supplied to the effort to do the plugin for Godot, and it's used there. So really, the heart of the matter in using Cesium Native is dealing with glTF, because that's what is going to be supplied to your application ultimately for the geometry and imagery in 3D tiles. And just recalling what glTF is, it's a JSON file, and the JSON objects are all kind of free-form key-value pairs. We'll look at an example in a sec. These are usually grouped in arrays. The binary data is not in the JSON because you can't do that, so those are off in external files somewhere referenced by the JSON. And then there's a special binary format which jams your binary data together with your JSON in a special way, which is actually a lot more convenient to deal with over the web. It's a format called .glb. This I stole from Marco Hutter's reference guide, but it very quickly shows what's going on in the JSON for glTF. We have all these arrays that have indices into other arrays. The nodes indexes into itself for the children of each node. Nodes contain meshes, goes off into another array. That contains primitives. That references stuff that goes off yet into other arrays, and then there's a whole chain of references to finally get to the binary data that's in a buffer all the way at the upper right. You can probably tell which arrows are my addition to this diagram. And so to get into the C++ and Cesium Native, we generate a whole lot of code based on the schema from the glTF spec. And we generate classes to represent the data as well as code to read it and write it from and to JSON. And in general, it's not very obscure. The JSON objects are C++ classes with optional fields are C++ optional values. And these are arranged in arrays. And sometimes we hang other pointers off these objects, for instance, to store images in a more convenient way than just the binary data that happens to be embedded in the JSON. And this is a very high-level look at the model, which is our representation of a glTF file. Really nothing magic, a bunch of vectors of objects that are themselves JSON. So when Cesium Native reads a glTF, it does a lot of decoding for you. One thing that is convenient is that the image formats are decoded into something that you could load to a GPU fairly directly. That is to say, simple things like JPEG and PNG are decoded to raw pixels, which can be uploaded. There's a bunch of support for compressed texture formats, and I'll talk a little bit about this in a second, but those are generally left in a format that would be directly supported by a GPU, depending on the compression format supported by your GPU. In order to make mesh data, for example, a bit more convenient to deal with, Cesium Native provides a thing called an accessor view, which is an abstraction of the accessor that is in glTF. And this is sort of attacks the problem of supporting polymorphism statically in C++, which is always kind of exciting. But it creates, it's a visitor that you pass a function, or a lambda in this case, which then gives you sort of polymorphic access to the data in that accessor. This example here, just very briefly, you can look at it later, is accessing the data for the quaternions that represent rotations in glTF and following one path if they happen to be floats, and doing something else if they're not, which is not really clear. Well, it is clear what to do, but it's rather complicated. But this is all just using C++ standard templates and some templates that are written for this application to eventually access the data as a float. When we see the line VSG rotate, we are finally dealing with floating point values there. And today, the problem of reading glTF is kind of complicated because often they are compressed in several interesting ways. There's a library called Draco, which is older now, and Meshopt is new and very promising. And you mostly don't want to deal with this in your application because it's kind of a distraction. But there are various options that go along with this, and I mentioned here, Meshopt can produce coordinates that are in integers, for instance. By default, Cesium Native will translate these to floats because that's what you want to see, but if your application is sophisticated enough to deal with the integer coordinates, you can tell Cesium Native to leave them in that format for you. And so there is a handy function to load a glTF in the glTF reader library inside Cesium Native. But it doesn't actually return a loaded glTF. And this is an unfortunate complication, but you just have to deal with it. And this comes from the fact that loading glTF is complicated. It could, for a glTF anyway, require Go loading other stuff from the network once it's loaded the glTF. And then there's a bunch of additional potentially lengthy work that needs to be done to finish the loading, this decompression I mentioned, and perhaps a bunch of other stuff. So this is all handled asynchronously through the Cesium async system. The result is that load glTF doesn't return a glTF, it returns an object that at some point in the future might yield a glTF. And the Cesium async library provides several functions for dealing with this asynchronous task and dealing with a bunch of them in parallel. Start a task, and it can run in one of several different threads. I say main thread or worker thread. I'll get to that in a second, why we care. And then really the biggest thing you see in the code is where you're going to deal with the result of one of these features once it becomes ready. And Cesium async sort of automatically provides the place for you where you will receive the results. And this thing about main thread and worker thread is something you see all the time in game engines and graphic APIs, where there's often a thread that's privileged for whatever reason. Either used to be an OpenGL, it'd be very tricky to load textures or load shaders in anything other than the main thread of an application. And in Cesium for Unreal, where this library was originally written, there's a whole bunch of things that just shouldn't be done off in worker threads. They have to be done in the main thread. And for that, we provide sort of this big distinction between things that happen in the main thread and things that happen in a worker thread. Other systems care much less, and it really is up to the author of an integration what to do in these, but that's where things get done. And then the features that Cesium async provides sort of come about by being told to be run in worker thread, for instance. And then the results are usually accessed in a method such as then in worker thread, which we'll see how this is chained together in a second, provides a natural place to receive the results of an asynchronous action. And we depend on move semantics in C++ to ensure that you're never trying to get the result from a thread more than once. This is a quick example from the VSGCS integration of loading a glTF file. I say return reader.loadglTF. That's returning a future. And right away, we chain a method invocation, which is then in worker thread, and then in that Lambda, finish up what VSGCS needs to do with a loaded glTF, which is, you see the model variable, well, that's the result from load glTF. Usually, you don't really want to wait on the result of a feature if you don't have to, but sometimes you do, and this is an instance of code where we wait. Generally, we would just wait, and everything comes to a halt, but sometimes we can't wait, like in the main thread, we don't want to wait, so we have to do a little bit more trickery there to kind of spin and accept that something's going to be ready at some point. The flip side of reading glTF is writing glTF, and this is a lot more basic in Cesium Native, but it's still very handy. And basically, if you fill in the model structure, which I showed a few slides ago, with a complete glTF model, then I'll be ready to go. If you want to produce a GLB, which I highly recommend, you kind of have to arrange it so that Cesium glTF writer can write this out, keeping everything in a single buffer and saving all the images into that buffer. But then write GLB gives you a string of bytes, which you then write out to a file, and there's your GLB. So now passing on to 3D tiles, which is kind of a more interesting subject in Cesium Native. If you have a graphical application, you really don't need to know about 3D tiles. You deal with glTF and some information about where they're placed in in space and images, and really that's it. However, if you do want to deal with 3D tiles, you can read them, read their contents, write them out. Cesium Native uses the same strategy for generating readers and writers for 3D tiles as it does for glTF. This is kind of a complicated subject because 3D tiles are, well, they can be really big. I mean, we have some huge tile sets, and loading the whole description in, is it useful to? Does the description actually contain all the tiles individually? Does it do some kind of implicit tiling? But I maintain this is still useful for smaller tile sets. We call these programs tilers at Cesium, and I think elsewhere you do too. So if you're going to write a tiler using Cesium Native, some things to keep in mind is that we don't actually have writers for a lot of the 3D Tiles 1.0 formats, like B3DM, for instance. There's not a writer for that in Cesium Native. But you can produce a useful 1.1 tile set because now GLB files are a valid payload for 3D tiles, and we can write those out without any problem. And you can walk whatever your model is internally to produce a tile set, and you create tiles and their children, put them in a tile set, and write them out, and it's great. Yeah, so it really is not that easy because real tile sets are huge, but you still can make good use of Cesium Native, both for the individual contents of your tiles, and there's really good support in Cesium Native for the latest stuff in 3D Tiles 1.1, including implicit tile sets, which is probably how you'd attack this if you were going to write out a huge tile set. So putting it all together in a real application, how would you do that? It's the whole reason Cesium Native exists, and Cesium Native does really the hardest part of that, which is figuring out what tiles might be visible in your scene and taking it from there. Every tile that's visible, figuring out the current screen space error in a view. From that, figuring out which tile to render. If the best tiles aren't available, then schedule loading that. Tell your application what tiles to render, and then finally get rid of tiles that are now unused, because you can't just keep the whole world loaded in your application. And the tile selection algorithm in Cesium Native is pretty hairy. It's unusual in that it tries to avoid loading the whole pyramid of LODs. It really tries to only suck down those tiles that are needed at any one time. And at the same time, as you move around, it uses the tiles that are available until all the children are loaded. But you really don't need to know this for your application. We do provide quite a lot of detail on the algorithm, but your client can ignore this, and this is the whole point of Cesium Native. So just a quick visualization of if you have part of the world loaded, well, here are all the tiles in a debug view given a different color. And Cesium Native has determined what tiles need to be loaded in this view. So if you want to write an application, you need to implement an interface called prepare render resources. And it doesn't do very much. It accepts a glTF model and a transform indicating where it's positioned in space. And it returns to Cesium Native an object with the data your application creates for the rendering, whether that's part of a scene graph or other graphic primitives. Cesium Native doesn't really care. It'll eventually pass it back to your application. We'll see. Again, there's this prepare and load thread, prepare and main thread split, and it's really up to the application what needs to be done in those two places, whether you can do almost everything in a load thread or whether there's some critical task that can only be done in the main thread. Well, that's where you do it. And there's a few more. Cesium Native can overlay arbitrary raster imagery on 3D tiles, which is kind of cool. And in order to support these, there are separate functions for turning these rasters into textures, for instance. Okay, almost done. One thing is, I didn't realize that Cesium World Terrain only includes height data. So if you're writing an application and you want to use Cesium World Terrain, you really need to implement these in order to have anything other than a snow white globe on the screen. One thing I didn't mention here is another thing is that Cesium, this interface has an interface for freeing data, which is necessary to implement. Really, the other main part is telling the application what tiles are in view, done with a function called updateViewGroup that produces a big list of tiles. These tiles do contain eventually the data that you created when you prepared the tiles earlier for when they were loaded. And then what you need to do with the tile data, well, again, that's up to you. Whether, because this is all in Earth-centered or fixed coordinates, they may need to be translated in your system, depending on your system. So this is a quick example from a client that uses Cesium Native and renders using Vulkan Scene Graph called VSGCS. This is a view of Paris of the Google 3D photometric, photorealistic tiles. And the strategy I would recommend if you want to write one of these yourselves is implement a glTF viewer first. This way, without much drama, you can figure out whether you can get anything on the screen at all. It's a very good first step, probably a good exercise. And then you need to figure out what to do with ginormous coordinates. Your rendering engine may or may not support them natively. After that, the interfaces of prepare render resources. It's really the heart of the application, but should not be much more work than the glTF work you've already done. And then additional auxiliary stuff, interfacing with Cesium Ion, which Cesium Native provides quite a bit of support for. Doing useful things, you want to load multiple 3D tile sets at a time. For instance, OSM buildings are a separate tile set. If you wanted to put those on Cesium Terrain, you'd have to have them both in your application. Not a problem for Cesium Native, but you just need some way to do that. And then quickly, we do require something in addition to just glTF. The instancing extension is required to get support for instancing from 3D tiles. The overlay support requires a simple extension of layering more textures and texture coordinates on your glTF. And some other things having to do with compression. And really the one insight that I learned going into all this is that the coordinates in glTF can in fact be Earth-centered. They can be huge. They're not just floats, and you'll need to deal with that. That's it.